Now, my question is, this is the kind of paged memory system where memory is divided into equal size pages. Programs are also divided, as a program comes in, is divided into equal size pages, and every page is located in a certain page frame. We have to look through this table that contains all the pages and whether the page is free or busy. So if we need 3 or 4 pages for a program, we go down to find free, okay, take its number, and put them in, map them here, and then keep going down, find another page, 3,500, another page. So the question is, if you are to do this, if you are just to manage this, would you divide these page frames or pages into large pages or small pages? Is it better to have larger pages in the memory, divide memory into larger pages, or smaller pages? Larger, and why? Of course, you know, easy to say smaller, larger, but why? You have a logical reason behind it.
So if the page is large, then the access memory will be larger. So it will be. Then
what memory is larger?
More free memory will be larger. So it will.
More free memory, you mean? Memory, let me say, total amount of memory is the same, whether you divide into large or small pages. Maybe at the end of every program, the last page of every program might suffer from more fragmentation. So you might lose more in fragmentation. The larger the pages, the more that's wasted as internal fragmentation at the end of every program. So that's a disadvantage. See, let's go for large size. That's a disadvantage of having or choosing large pages. But it's okay because you're given the program exactly the same memory as it needs normally. Whether you decide every page is 500 or 100 bytes, you just end up giving it more pages, but only the last page that, if it's 1,000 or 10,000, then the last page that's only needs 300 bytes. You know, it might, if the page is 5,000, then there's a lot of internal fragmentation. So generally, then smaller pages are better, because smaller pages, even if there's fragment left, there'll be very little. If a page is only 100 bytes, even if you only put 1 byte in it, you're only losing 99 bytes, which is not a huge amount. So in general, it's better to go for smaller pages. But what's wrong with smaller pages? Let's go for very, very small pages. So we only have 10 bytes in every page. What's wrong with that?
It's more difficult to manage them.
Why would it be more difficult? They are all equal size. We can still always do the multiplication. They are uniformed in size. It doesn't matter whether they're 10 or 100. You can jump to any page you want. Any location of the program, you can find out. If we only gave it 5 pages, we know it's going to be in page 3. If we gave it 50 pages, it's going to be in page 35 or something like that. So
the total number of jumps would increase.
Okay, yeah, we'll be going from one page to another, but we don't really have a major issue finding where the page is. Yeah, there'll be slightly more, but not to a point that affects the performance. Anybody else? Okay, remember, if we split this into 100 pages, then you're going to need a table of 100 pages, 100 records. If you split this into 1,000,000 pages, you're going to have a table of 1,000,000 records to manage those 1,000,000 tables. So you might be saving a bit of memory on that, but you'll end up using that extra memory to manage it, to have this table. This table might by itself take a lot of space in memory that you're trying to save. So very small size pages is great. It will reduce the internal fragmentation, but it will cause you losing a lot of memory just on the table itself, because the table is going to be very large that you're going to need to maintain for each individual page. Remember, you need to have a table for each single table that has a record for every page in the memory system. And if you have more, then this table is going to be more. It needs more memory, and memory is something that you're trying to save. So in general, it's better not to have very large pages and not very small pages. Maybe experience will try in a few different pages and see how the performance operates. So it's just a question that sometimes it's asked. Remember, guys, anytime you ask a question, which one, there is no clear answer. Never say, okay, this smaller pages are better or larger pages are better. No, each choice in technology has advantages and has disadvantages. But don't ever give your opinion and you say system A or method A is better than method B. Never. Always say, well, if you go into a company and they say to you, well, which one shall we do, this or this? Shall we use fiber optic cables or twisted pair cables for our network? Don't say, okay, fiber optic cables are better because they're faster, they use light. Yeah, maybe, but they may be more expensive. Or maybe there's so many other things. But the point is, always say, well, this approach has the following advantages or problems, and this approach, like sometimes cost. Sometimes we know this technique is better, but it's very costly, and the company does not have the resources or the money to do it. So you have to tell them, that's a good approach, but it's very expensive. This is maybe a less cheaper approach or a bad approach, but it's affordable. You can afford it, you can run things on it. Anyway, so let's go to the next system. So what's the advantage of this system compared to the previous systems, and what's the disadvantage? This system does not have any external fragmentation, just like dynamic partitioning system, which is great, doesn't have any external fragmentation. But the dynamic system has a problem of too much external fragmentation, and it cannot be solved out without compaction, and compaction is very slow. This does not have any compaction function, and it doesn't get into a slowness kind of thing. As long as it works, you can put in a program. The disadvantage of it is that still, like the previous systems, you need the full program in memory. So if your memory can accommodate 10 programs, that's it. You cannot run any more than 10 programs. That has not changed. But we can run it more efficiently and faster and better than the previous systems. But still, it suffers from this problem of not having, or of not being able to run more programs than the previous systems. And hence the next system we're going to be talking about now, and that's called virtual. The next system uses something called virtual memory. So this is the last system we'll talk about, which is number 5. It's called demand paged. So the last system was called paged system. Paged memory management system. That means just basically pages. Divide your memory into pages and use them. Give every program as many pages it needs. The next one is called the demand paged. Demand paged, that means only give pages that as needed. So this came after the invention and improvement in operation and performance of hard disks. In the past, there were no hard disks. We had no hard disks. The only storage device was tapes. And in tapes, if you want to read something from the end of the tape, you can't just jump straight to it in 1 second. No, you have to start reading from the start until you reach that piece of information you need, which could be at the end of the tape. So it could take you a few minutes before you actually reach the end of the tape. So tapes as storage device cannot support interactive systems. Remember, interactive system needs quick response. If your data is on a tape and a user says, okay, show me that data, you might have to wait for 3 or 4 minutes before you can actually read it from a tape. That's provided the tape is already mounted on the machine. Because if it's not, then it could take a lot longer. If a person has to come in and install the tape or so hard disks came out, and hard disks are fantastic devices. The point about hard disk is you can read from anywhere on the hard disk within almost the same amount of delay. There's no difference. With tapes, no. If you are reading from the start of the tape, you'll get the information quicker. If you want to read from the end, it'll take a long time. Sometimes if you go past the piece of information, say, can you go back and read it? In tape, you cannot go back. You have to go back all the way to the start and start reading again until you read it. Only one direction reading. So tapes, even though they're very cheap and they store a lot of information, so like this the question again, when we start doing device management, I'll be asking you which one is better, a hard disk or a tape? And of course, a hard disk you can read from anywhere you like. A tape you can only read sequentially. Hard disk is faster, tape is slower. The answer is automatically going to be, yeah, of course, hard disks are better. But that would be a wrong answer. Because tapes, yeah, they have disadvantages, but they're very, very cheap. They can store a huge amount of information compared to hard disks at a fraction of the cost of a hard disk. They still use a lot of them in many organizations and companies. Backup operations that does not require somebody sitting waiting for it. You start it at night and they start writing all the information to tapes, maybe in a different country altogether. And you back it up and you may never need to read it. Only if disaster happens and you lose all your information or an earthquake that damages all your computer center, then you have your tapes in another place and maybe recover it. But anyway, that's not our topic today. But the topic is that when hard disks came out and they started becoming fast, and even though they're relatively fast, because as far as the CPU is concerned, they're still very slow, very, very slow, because they're a mechanical device. A hard disk rotates at a speed of about 15,000 revolutions per minute, and the head goes to anywhere and can read the information. All the information is written on tracks, on circles, on the hard disk. So the head goes to any circle it wants, and the circle goes underneath it in a kind of a fraction of a second. But still, as far as CPU is concerned, it is slow. But we can read any piece of information within a second or two, we have it. So that's the fastest thing next to main memory. So they said, why don't we use the hard disk as an extension of memory? We cannot use it as direct memory because it's a million times slower than the speed of CPU. It won't do. But we'll use it as an extension, but not as main memory. And remember, just so you know what the difference between main memory and auxiliary memory or secondary memory. The hard disk is considered secondary memory. And a secondary memory, just like books in a library, they are considered part of your secondary memory. Like you don't have any of the information in the books that are in the library, but if you need it, you can go open a book, transfer the information to your head, and you can do whatever that book says. Like if it's a formula, you can read it to your head and then start implementing it. If it's a recipe to cook something, you read the book, bring the information to your main memory, and then execute it. That's how things work. Same with computers. Computer has its main memory that can deal with the CPU. Your brain is like the CPU, and the memory around your brain, whatever it is, that's the one that the brain can reach it quickly and bring it back and analyze it or process it. So same with computers. Computer CPU has its main memory beside it so fast, almost speed of light. It exchanges information with memory. But with a hard disk, it's not that fast. And therefore we consider hard disk a secondary memory. Just like a library that's full of books to you, to your brain. That's your secondary memory. It's there. If you need it, you can open the book and read, but it's going to be a very slow thing. But once you get that information in your head, that's your main memory. So computer, this is the way they decided to do it. We have memory, but we want to run more programs. Well, we cannot do it so far with the page system that we had. Remember, it's an extension of page system. So we have memories divided into equal size partitions called pages. They're all equal size, not too big, not too small. And any program, we can load it If we want, we can load the full program anyway. As long as there is a free page, we can upload the program. But we don't want to upload the full program because many times the code that you write in a program, it never runs. There's a lot of code that programmers write and test and everything, and then it never runs. For example, they take care of situations that never happen. Whatever the situation is. For example, you say, okay, you have a computer that controls the operation of a car, but say in the case of dirty fuel, this is what we will be doing. And you have lots of code written for that situation. But so far you've been running this system for 5 years and never had a problem of dirty fuel. And therefore that code you keep bringing to your memory, you never even call. Or error detection, for example, not error detection, but error messages. You ask a user to type in their date of birth. They write a date that's more than 100 years ago or in the future. You say, sorry, this is wrong. So that function of error in the date of birth, call that function to run. You've written some code to communicate with the user, but no user so far have written the wrong code, and therefore that program is being uploaded every time you run your program and it's never used. So remember that there's a lot of parts of many programs that are never used. So now we say, why should we bring those codes into memory? And also remember the CPU, it can only run one instruction, one line of code of one program. And your program could be 100,000 lines. Why should we bring the 100,000 when we are only doing one at a time? Can we bring 10,000, let it work, and then if we need the next 10,000, we can go and bring it. So this is the general idea. They said, the advantage of hard disk is that we can reach any part of it. It's called random access device, just like main memory, it's random access device. But the other good thing about hard disk is that it has a huge size, almost unlimited space compared to main memory. So imagine this is a hard disk. And since the year 2000, they've been using this kind of system. It's known as virtual memory. So they use the hard disk as if it's real memory. The word virtual means almost real, and not real though. So they use the hard disk as if it is memory, even though it's not really 100% memory. Just when you hear about virtual reality, you're playing a game, you're almost, you can think you're in reality, even though we know it's not. It's just virtual reality. Same as this one, virtual memory. So can we use the hard disk as part of memory? Yeah, we can use it because it's a huge amount compared to main memory. So imagine we take few of the tracks and we say, okay, those tracks, let's use them as memory. But for now, I'll just say, I'll take this part here, right? It's not exactly, the way it's done, but. So let's say you have few programs on the hard disk. You say, all right, we want to run one of the programs. So instead of loading the program into main memory, we load it into this part of memory that we say, okay, this is the virtual memory. This part here. This hard disk, usually when you set up Windows, since the year 2000, you set up Windows, it will ask you how much of your hard disk you want to allocate as virtual memory. And most of the time it's 8 to 12%. You can change it though, but if you just take the default, I think the default is 12% of your hard disk is allocated to memory, to become virtual memory. So this is what we do. We bring any program that needs to be executed. It's not brought into memory, it's brought into another part of the hard disk that we call virtual memory. And it's divided into pages. This program could have 30 pages. Or 10 or 12 or whatever. And we only bring 3 or 4 of them into main memory. So this is the real idea of virtual memory or demand pages. That means we only bring the first 3 or 4 pages, 0, 1, 2, and 3. In fact, we only bring 1. But we allocate you a space, for example, the memory manager decides, maybe that based on the size of the program, or based on the priority of the program, how important the program is, or based on so many other points, but it doesn't matter. Let's say it gives every program 4 pages, or 10% of its whatever its requirement number of pages it has. Like, stay with me for a while, guys, for a few minutes, and Once you understand this, you'll have no problem answering any question, hopefully. And hopefully you never forget it for the rest of your life. So don't, anyway. So we bring in one page. Let's say the program, when you start running, the memory manager will say, okay, I'm going to give you 4 pages. Here it is, this one, that one, this one, and that one. Whatever, it finds any 4 free pages. I'm just going to stick numbers onto them. Page number 500, page number 673, and page number whatever it is, 800, and page number 905. It's just random numbers, but they are in sequence. And remember, the operating system is sitting there. Same thing as page system. But the program is not fully loaded. Not all the pages of a program are loaded. In fact, none of them are loaded at the start. But we tell you, here are the 4, this is what we are going to give you. It's like you book 4 rooms. You have a big party. You're like 50 people or so. They want to go on a holiday. You call a hotel and you book 4 rooms. That's all you have, 4 rooms. Or you want to book more, but they tell you, no, we only have 4 rooms for your party. So you can use them interchangeably. So anyway, so we bring in the first page. Page 0 is brought into this part here. So, we need to have a table again for every program, the pages on every program. So this is job number 1, or program number 1, but I'll call it job 1. It has 30 pages or 12 pages. Page 0, 1, 2, 3, 4, 5, 6, 7, 8, and so on. Let's say just 10 pages. Okay, and then first thing is the status. Where is this page? Is this page on main memory? Yes or no? Yes, 0 is yes, but the rest of them are all no at this stage. Okay, so we brought page 0 into main memory. Where did we put it in main memory? Which page? We put page 0, where is it? This is page 0, into page 673. So we know where that page is. If you want to go to it, you come down here to the page program table, page table for this particular program. Every program we upload has its own table, smallest table. Just has as many records as how many pages the program has. Page 0, yes, it's in main memory. The rest of them, no, they're not in main memory, they're on virtual memory. Okay, the one that's yes, where in main memory, it's in page 673. So we go there and we copy the code there and we start running it. So this is the code is filling. Of course, there's lots of code, in every page is full of code except the last one. But this one starts running. Let's say while it's running, it says, I need page number 5. You don't necessarily be running, executing page 0, 1, 2, 3. It doesn't matter. You can have a function that's already in page 5. So let's say this one says, I need page 5 on the program. So the memory manager needs to transfer your control to wherever that code in main memory is. So it needs to go to the main table, to the program table, say, where's page 5? There it is. Is page 5 in main memory? The answer is no. No, it's not. Well, then we better bring it over. Right, do we have a free page allocated to us that we have not used? Yeah, we have 3 more. We have only used 1 page. Well, then go straight and bring page number 5. So page number 5 is brought in, and there it is. So this is page 5. This is page 0. Okay, then the next thing, page 5 runs. It might say I want page 0. It might say we need page number 2. Where is page number 2? We go down there. Is it main? Oh yeah, but when we brought page 5, we mark it here on the table. Yes, now it's in main memory, and it's page number 500, just in case we need it later on. Now, page 5 said I need page number 2. We go down here. Is page number 2 in memory? No, it's not. Well then, can we bring it over? Do we have a free page? Yes, we still have 2 more pages. Well then bring page number 2, and there's page number 2. We placed it here. So this is page number 2 of the program. It's put in page number 800 in memory. Okay, do you see the way it works? So it's another reasonably simple system to manage, but we don't have to bring all the pages. We only bring them on demand. See the name of the thing? Demand page. So if we need the page, we go and bring it. If we don't need it, leave it there on the hard disk. Now, page number 2 runs and then says, for example, I need page number 4. So is page number 4 in main memory? No, it's not. Well then, do we have a free page? Yes, we have. So go and bring page number 4. So we bring page number 4 in there. And we put it in 905. And now, yes, it's in main memory. The rest of the pages are not in main memory. Page number 4 runs. Imagine if it says, I need page numbers, what's that? 5. I need page 5. So the memory manager goes to the tables. Page 5, is it main memory? Yes, it is. Great. Where in main memory? Page number 500 in main memory. You cannot even work out exactly where is this address of page 500 in main memory. It's just multiplied into the page size and bring you straight here. But let's say that's already easy to do. So let's just go to page 500. So we start running again here. Let's say this page here now says, I need page 3. Page 3. I need page 3. So page 5 says, now I need page 3. We go to the table. Where's page 3? Is it in main memory? No, it's not. Okay, we want to bring it over. Do we have free page? No, we've used all our resources in memory. We need to bring page number 3. Well then, now, let's pick one of these pages, write it back to the hard disk, to virtual memory, and bring page 3 in its place. It's like you go like the 20 of you, and you rent only 4 beds in a hotel, 4 bedrooms. Every bedroom has 1 bed. If you want to go to sleep and they are already full, those rooms are used, you have to wait until, or we go and wake one of them up and say, excuse me, can you leave now? And we use your room. That kind of thing. Imagine that's the situation. So yeah, we have 4 users, 4 pages are in main memory. We have to take one of them out. Later on, we'll figure out which one of these pages is the best to take out for better performance. Which of those pages? Will we take the page that we moved into main memory first? That's called first in, first out. Or shall we take the last one that was brought in? We'll find out later on which one is better. But I don't need the answer. Let's just get the main idea first, and then we'll work on how to improve it. So now, let's say we decide, okay, let's take page number 5 out. Page number 5, maybe it's an error function that we only needed once, we never need it again. Or sometimes the initialization procedure in every program. Something you do once at the start of the program, never need to do it again. That would be a nice one to take out, because it's just sitting in main memory doing nothing. Anyway, it doesn't matter. We'll find out later on which page to take out. But let's say we decided, okay, let's take page 5 out. So we take page 5 out, write it back to its original location, overwrite the one that's there, because sometimes the information change in here, in main memory. You say x equals 0, that's you've changed it. It's not the same as what's in the start of your program. But anyway, so once we write page 5, now we can bring page whichever, and we go to page 5 and we mark it, it's no longer in main memory. And we bring page number 3, yes, it's in main memory, and it's in page 613 or 673. And that's the way it works until the end of the program. Now page number 3, for example, works for a little while, and then says, I need page 1. Is page 1 there? No. If it's not there, we call that a page fault. So if you are asked, what's a page fault? When a page is requested, is demanded, is needed, and it's not in main memory. It's on the hard, of course it's on the virtual memory. All pages remain on virtual memory. We bring a copy and sometimes we write it back. If it's not in main memory, it's a page fault. Then we stop and we do the swapping. We pick one to take it out. Let's say page 3 said I need page 1. Page 1 is not in main memory. So we have to pick one of them. Let's say we picked number 2. So write 2 out and bring number 1 in and modify the information here. Number 1 is brought into main memory and number 2 is no longer in main memory. And we copy it here and we start executing. And we keep doing that until the program finishes. We keep swapping. Every time there's a page fault, we have to stop for a little while. And the hard disk is probably spinning and we read from it. But remember, the hard disk is a mechanical device. It's a very slow device. So things are really slow as far as the CPU is concerned. We wait, we leave it. It's something like you need input or output. You need something from a hard disk. And we go and give the CPU to someone else. But still, that means we're slowing you down. If you did not have a page fault, you'd still be running, executing. So when we run our programs in virtual memory, it has this problem of page faults. And the more page faults you have, the more delay is going to happen. Why? Because you're going to deal with this primitive device that we call the hard disk, that as far as the CPU is concerned, it's as fast as a horse compared to a rocket or a spaceship. So that's the difference between the speed of the main memory compared to the speed of a hard disk. So remember, every time we need to go to the hard disk and bring a page over, and remember, it's not just bringing a page over. At the beginning, just bringing a page over, but now if we need a page that's not memory and there's no room for it here, we have to take one of these pages, write it out, and bring the page, read it in. So you have two operations with the hard disk, a write operation and a read operation from the hard disk. So if you have plenty of page faults, it's a bit of a problem. So things are going to run very slow. I'll give you one example of how things can run very bad or very slow. Imagine, have you started programming, guys? Yeah? Okay, good. Virtual memory is just ordinary hard disk surface. You store information onto it and you're reading it. The only good thing is that you can go to any location and read it randomly. And it's reasonably fast, probably so far one of the fastest ways of reading memory, but still compared to the CPU or main memory is very, very slow. So it's better not to use virtual memory if you can have plenty of main memory. But there are technical problems that there's a maximum address you cannot exceed maybe unless they increase the bus type. You know, when we talk about the address is moved in 8 lines or 16 lines or 32. When you buy your next computer, it's probably going to be 64 or maybe 128. So the whole design sometimes limits your number of addresses. Sometimes you can have a lot of memory in your machine, but your address bar can only address a certain amount and the rest of it cannot even be addressed. So memory has a lot of problems, technological, and not just, it used to be difficult to make memory, but when we started making a lot of memory, then how are you going to be addressing each one of them? You need the address bar. Remember when you move data, we say, bring that instruction, put it in the CPU. You have to tell it where is that instruction, the address. And the address is something called the address bus. When they made the computer first, there were 8 lines, so that the maximum number you can write is in 8 bits. But then they increased them 16. So when you buy your laptop, you're going to, even now, say when they are installing Windows or running some programs to tell you, listen, we can only run it from 32 bits. That means you have your address memory can move in 32 bits inside the bus of the board. That means you have bigger number of addresses and things move faster. Sometimes you say, no, we need it to be 64. So there are a lot of technological issues. You can't just say, okay, I'm going to use unlimited. From the hard disk, it's solving a problem for now. But in the future, I'd imagine we'll be able to have even more memory and address it better. It's going to be a lot more efficient and faster than hard disks. But since the year 2000, it's used a lot, virtual memory. Anyway, so now I'm going to show you a problem where we can have a lot of page faults. So let me ask you first, what's a page fault in virtual memory? Any idea? Do you remember? Anybody here remember? What's a page fault? Anybody was listening to me? Yeah? Yeah, when a page is requested or needed, but it's not in main memory, it's on the virtual memory. Then we have to stop executing, we have to go to bring it. If it's in main memory, we just transfer to it and we start running. But if there's a page fault, then it's not in main memory, we have to stop. And as far as CPU is concerned, you'll probably be stopping for decades. But CPU, it works so fast that we have to call this hard disk, this slow thing to bring us that page. And it will go and do, hopefully work. serve some other application until you bring it. So we can live with few page faults, but not if it happens each time. And the worst thing is if you take a page, remember in page fault, what happens is that sometimes your page is running, say this one is page number, I don't know, whatever page number it is, page number 5, and it says I need page 2. Or I need page 8. You go and bring page 8, but there's no free page frame here in memory. So we say, okay, pick one of them. Which one will we pick? Let's say we picked number 2. So we write 2 out to bring number 8. Imagine if page 8 runs a little bit and say, get me page 2. I need page 2. We just took it out. Yeah, I need, we need it. So we have to pick one of the pages here and say, bring page 2. You might be our policy is the last page you brought in, get rid of it. So with the last one we brought in is 8. Well then, let's take it out and bring number 2 in there. And number 2 runs a little bit, say I need number 8. And then you run 8 and say I need number 2. So you keep swapping those 2 pages. And that's an example of where you get a lot of frequent page faults. And that really brings performance down a lot. But there's another one, or the codes sometimes are like this. How do you write a loop? How do you write a loop that runs 10 times or 1,000 times? Anybody can give me the code for that? 4. Yeah, go on. Here's x equal what? And then 4, x equals
0.
Or while 0 to 1,000. Did you guys write any code of a loop?
Not like that, but
Okay, give me a style, all right. Okay, let's say print x, or not print, just x equal x plus 1, or t equals t plus x. T equals t plus x, and here t equals 0. Right, this is your code. T equals 0, I'm gonna get you to add, x is gonna have 0 and then 1 and then 2, and each time you add that to a total, and this t is gonna have 1 added to it, and then 2, 3, 4, up 1,000 times, and then next x. See this program? This will run 1,000 times. It will start giving x the value 0. Stay with me. Leave her alone.
Thank you, sir. Thank you so much.
So if x equals 0, and you go run through the loop, then x equals 1, x equals 2, 3, 4, until 1,000, and then it goes print t. What do you think it will print? T is going to have the value 0, and then we add to it 1, and then plus 2, plus 3, plus 4. We keep adding all the numbers from 1 to 1,000, and when we come out, we print t. So this is a simple loop that runs 1,000 times. It'll run in less than a second, and it'll print a value there. But imagine if your program, this is just part of your code of thousands of lines. Imagine you divided this program of yours into pages. And the page, every page, for example, 100 lines. So the page end came at this point. That's page number 5. And this one here, page number 6. Okay, and the rest of the code, page 7, 8, and all that. But I just came at this loop. This loop got split in half between 2 pages. So imagine if we are running page number 5 in there, in memory. Say page number 5 is running, wherever that page, no, that default page. So page number 5 is executing here. It got to the end of the line. It just executed for I equals 0, and then it's going to increment it and all that. Now, got to the last line. Now it needs page 6. So imagine if it calls, I need page 6. That's the last line in page 5. Page 6 is not in memory. That's a page fault. Just go and bring it. To bring it, we have to take one of these pages out. if our policy decided to pick page 5. So we take page 5 out, bring page 6 in. So now page 6 is running. Page 6 runs one line, and then the second line says go back to the start of the loop. The start of the loop is in page 5. And it says go and get me page 5. That means we have to stop. Page 5 is not in memory, we just took it out. So we need to bring it in. In order to bring it in, we have to take one of those 4 pages out. Let's say we picked page 6 to take out. So we take page 6 out, write it, and upload 5. 5 runs this line, and then the next line says I need page 6. So it's just because we are so unlucky. We split at the end of our pages. The separation between our pages came in the middle of a loop that's going to run 1,000 times in less than a second. So, but that's if it was just in one page, it would run less than a second. But now, each time we want to go to the hard disk, write one page and bring the next one, it might take a second at a good hard disk. That means we're going to do this second 1,000 times. So we're going to have 1,000 seconds just inside this loop that we could have done it in 1 second. So sometimes paged system or virtual memory that uses demand page system, the way we've done it here, lovely pages, all split, divided, and then we only bring a few of them into memory and swap them if we need it. Sometimes we are unlucky that our pages are split in the wrong place, especially in a loop. You have a loop for 1 to 100, 1 to 1,000 or something like that. And we use loops a lot in programming. So if the split comes in the middle of a critical section like this, that we have to end up swapping those pages so many times, that can cause a major delay. So that's one problem with demand page systems. And we'll see how they improved that, got rid of that problem by saying maybe equal size pages is not such a great thing after all, because it pays no attention to the design of your program or the logic in your program or the loops or whatever, like especially a function that you need to do it, all the complete function, but you end up splitting it into 2 different pages, and that can cause a lot of page faults. So what we'll do next week is first, we look at the best policies. Which page would we take out? If we decide we need to bring a page from virtual memory, but we have to take one of those pages out, which one is the best one to take out to reduce the number of page faults? So the number of page faults, we'll use it as an evaluation of which policy is good. We run a program, we see how many page faults we got. Remember, every page fault costs you a second. Normally in a second you'd execute 1 million lines of code. You could finish your programming in a second. But if you had 10 page faults, that can cause you a long time, delay time. Or you can have, like if it's in a loop like this, you could end up having 1,000 page faults. So we'll find out the best, which of these pages will we pick in order to reduce or minimize the page faults. So virtual memory is great, but it has this disadvantage of page faults.
Is the number of active pages that you use in main memory fixed?
It's not fixed. You can, no, it depends on the system. You can decide, okay, say if a program has 100 pages, I'm going to bring 20 in. But let's look at the worst case. This is the next thing. Is it better to give every program large number of pages in memory? Like in this program, we decide to give it 4. Is this a good number, or should we give them more to every program or less to every program? That's the next question. If, for example, look at the extreme. Anytime somebody asks you, is it better to go for more of this or less? If you want to see the difference, look at the extreme. Give a lot to this. When you say more, don't just add 1 or 2. Give it a huge amount and see, does that make a difference, so we can see the problem immediately. Or if say give it less, give it 1, the minimum, the absolute minimum, and see what difference does that make. So look at this program. Imagine if instead of 4, we only give it 1. You only have 1 page in main memory. Do you think we're going to have more page faults or less page faults? So this program brings page 0. After a little while it says I need page 2. It's not in main memory. We know it's not in main memory because 0 is there. So I have to take it out, bring number 2. Number 2 runs and says I need page 5. That's a page fault because page 5 is not in memory. We only allocated you 1 page frame in memory. That means if you give programs less space in memory, in main memory, you're going to have more page faults. Things are going to run slow. Yeah, you're going to be able to execute maybe 200 programs simultaneously, maybe even 1,000 programs. But every program is going to have, so every page it needs, it's going to be page fault. It's going to be performance is really, really bad. If you only give every program, allocate them 1 space in memory. Every time you need another page, it's a page fault. Or sometimes say, let's give more. What if we give more? The biggest you can give any program is all the pages it needs. But if you give every program the pages it needs, it'll never have a page fault. If this program is fully loaded into memory, we'll never have page fault. But that's like page systems. It works perfect, so fast, no delay, no page faults. But what's the problem with that? What's the problem? We've given every program as much memory as it needs. So it will have 0 page faults. You have 20 pages, here's memory. We give you 20 pages in memory. Your program is 30 pages, we give you 30 pages in memory. So anytime you run, you'll never find a page that's not in main memory. All your pages are in main memory. So you're never going to have page fault. And therefore, you'll work really fast. Every program will work fast. But what's the problem with that? What's the problem with this good speed that we can have by giving every program all the space it needs in memory? Give it as much space as it actually needs. Not needs, all its space. If a program has 40 pages, give it 40 pages in memory. If it has 12 pages altogether, give it 12 pages in memory. What's wrong with that? If we do that, then memory will fill very quickly. You can only run maybe 5 programs or 10 programs. But if we only allow, if every program comes in and say, oh, you have 30 pages, give us 3 only. If we only take 3 or 4, give every program 3 or 4 page frames in memory, we can run hundreds of programs. Because every program is only part of it is in memory. So we can run more programs, but remember there'll be a lot of page faults. So it's a choice between running more programs at poor speed, suffering from page faults, or running less programs, but at higher speed, with less delay. So the choice is ours, but obviously we needed virtual memory in the past 20 years. Maybe in the future we won't need it. We'll have a lot of memory. Memory is becoming cheaper and more technologically usable. Thank you very much, guys, and I'll see you next week.